Hello and welcome back to the video lecture series on statistics for machine learning. This is Amit Das, and we are going through the definition of probability, which is a very important thing in the theory of probability. And we have already seen the classical definition of probability. What's the classical definition of probability? For an event A, the probability of event A is defined by the ratio of the number of outcomes favorable to the event divided by total number of mutually exclusive, exhaustive, and equally likely outcomes. So total number of possible outcomes. So that is n. So this ratio m by n basically gives me the probability of the event A. This probability is also called a priori probability of this definition. Why is that so? Because the outcome, or rather the likelihood of a particular event is not influenced by the occurrence of a prior event. Just to make a very layman's understanding, so when, say for example, I am looking at the event E1, which is tossing of a coin and getting a head, right? I mean, the random experiment is tossing of a coin, and the event E1 is basically having a head as an outcome. Now, when I do this head, when I do the probability of this outcome of this event A, it doesn't really matter whether in the previous random experiment outcome was a head or a tail, or the event E1 did occur or not, right? So it really doesn't matter because the outcomes are equally likely, right? So this definition is known as a classical or a priori definition of probability. Now, when I want to calculate the probability of an event A, what do I need to do? So basically, I need to do very simple things. First, I need to find out the value of the numerator, which is the m, which is basically outcomes favorable to that event. Then I need to find out the total number of outcomes, which is n, and then I need to find out the ratio of m and n. So divide m by n. So obviously, one thing you can understand, it's very self-explanatory, that m is always going to be less than or equal to n, right? Because number of favorable outcomes can never exceed the total number of possible outcomes, right? And minimum value for n is going to be 0, right? I mean, if there is absolutely no favorable outcome at all, right? So the value of the probability, so if I just divide this by this m by n, I mean, so this one by n, this one by n, and this one by n, right? What do I get? So basically what I get is 0 less than equal to the probability of whatever event A, say for example, is less than equal to 1. So the value of probability is always going to lie between 0 and 1, that is given, right? This is self-explanatory, but just I want to very clearly state it out. Also, if there are two events which are like exhaustive events, say A and B, right? There are two events. They are like exhaustive events. So obviously, what you can also say is P of A plus P of B is equal to 1, right? Because there cannot be any outcome which is not favorable to A and also not favorable to B, because A and B are mutually exclusive. Sorry, they are equally, sorry, they are exhaustive. So the outcomes need to lie either as a part of event A or as a part of event B. So PA plus PB is equal to 1. Anyways, let's leave this for the time being. We are going to cover the theorems related to probability shortly, and there we are going to cover all this, right? So this is, I think, a very simple thing that we can understand. Now let's take other than rolling of die or throwing of coin, let's take another simple example how we can calculate the probability of a particular event. Now, say for example, a family has three children. Okay, a family has three children. Okay, What is, if I want to calculate the probability that their birthdays don't lie on the same day? Okay, so three children, I want to find out the probability that their birthdays don't fall on the same day of the year. Okay, and assuming that it is not a leap year. Okay, so I'm just assuming 365 days. So what is the total probability? Again, the events A means the birthdays don't lie on the same day of the year. Okay. So first I have to m by n is the probability. What is n? All possible outcomes, right? And what is n? The number of favorable outcomes. Let's now calculate the values of the two things. First, let's calculate the simpler one. What is going to be n? N is going to be, for the child 1, I have 365 possible options. It can lie on any of the 365 days. Same for the second child. It can lie on any of the 365 days. Same for the third child. So it can be lying on any of the 365 days, right? So n, the value of n is going to be 365 cube, right? Cube of, cube. Okay. Now we need to calculate the value of m. What is the value of m? So let's assume the first child. First child can have his or her birthday on any of the 365 days. So let's assume it as 365, the number of possibilities. It can be Jan 1, Jan 2, Jan 3 to December 30, December 31, any of these days. The second child can be having the birthday on any of the 365 days, barring that one day on which the child 1 has his or her birthday. So how many options do we have? 364. Now let's talk about the third child. Again, he or she can have the birthday on any of the 365 days, barring the days on which either child 1 has a birthday or child 2 has a birthday. So 363, right? 363 is the total number. So 363, 65 multiplied by 364, okay, multiplied by 364 multiplied by 363. Okay, this is the numerator, right? Now, if I do the maths, if I just simply use the calculator and do the maths, okay, what's the probability going to come as? So, I have, so 365 by 365, I can just eliminate one of the 365s, right? So, I just do a 364 multiplied by 363 divided by 365 divided by 365. This is my probability. So 0.9918, I can assume this. Okay. So my probability is going to be 0.9918. I'm just rounding off. So this is my probability. This is how I can do the calculation for probability. So in a nutshell, if you just think about it, whenever you are trying to calculate the values of m and n, you can use the simple counting techniques. You know the counting techniques, permutations and combinations. So you use those concepts to find out the values of m and n. Once you have found those values, then you can just divide m by n. That's it. Okay. Now, couple of things I just wanted to say as closing notes before I close on this part of probability. See, one big problem about the classical definition is it always considers that the outcomes are going to be equally likely. Now, when I'm saying equally likely, this term basically means nothing but equally probable, right? So, that's why you can consider that this particular definition is kind of a circular definition. I am trying to define probability by using the word probability. Equally likely means equally probable. So I'm using the term probability, I mean the probable, in defining the probability. So that's one criticism which is there. The second thing which is also a big criticism is when the number of the value for m or n becomes countably infinite, okay, then we have a challenge. So all these things are going to work well when we think about a particular event where you can get a finite number of possibilities, right? A finite number of outcomes. Whenever it grows into a state that the possibilities or the outcomes are infinite, we have got a challenge, right? So that's another criticism about the definition of probability, or the classical definition of probability. But again, I think we need not break our head on this one, because we just want to understand the concepts of probability which are relevant in context of machine learning. So I think if we just understand how the probability is being calculated for a particular event, I think that is more than sufficient. Okay. So when we come back, we're going to talk a little about the different theorems of probability, which are going to also have a role to play when we talk about the more intense concepts related to the inferential statistics, right? So we're going to cover that as a part of the next lecture. Thank you. Stay tuned.